Okay, so let's chit-chat about this whole idea of stoichiometry that we started with yesterday. So, and I cannot emphasize this enough, okay? If you understand that the coefficients represent moles, not mass, life becomes much simpler. So, the common currency is moles, okay? But you always, at some point, you have to do a mole-to-mole ratio. So, if you look on that back side, you have this reaction between aluminum and hydrochloric acid. And you get 2AlCl3 plus 3 hydrogens, okay? Now, so here's the deal. The bigger picture is that if you start at the beginning, this whole equation is balanced because of the law of conservation of mass. Hey, however much of the reactants is how much products that you have to have, okay? That's where the whole thing starts. It's the beginning of the story. So if you were to see this reaction actually take place, you would have a beaker with hydrochloric acid in it, okay? It's a liquid. You drop in a chunk of aluminum. The aluminum would dissolve because of the fact that it's a redox reaction. The aluminum is giving up its electrons. It's going from the elemental state into the solution. And you would see bubbles of hydrogen gas form. Okay, that's what you would see. So you would see the aluminum dissolve, and you would see bubbles of hydrogen gas. There you go, simple reaction. Y'all have done similar type things. You've dropped zinc in hydrochloric acid. You've dropped magnesium in hydrochloric acid. Okay, you know what this looks like. And the only reason this takes place is because aluminum is more reactive than the hydrogen is. So basically, the hydrogen comes along because that's soluble, okay? So on an atomic level, the hydrogen comes along, it's missing an electron, it comes up to the aluminum says, take my 3 valence electrons, Eddie, Edna, and Edwin, I don't like them anyway, take them, I want to go be in the solution, boom, it happens, the little hydrogen bubbles form, they said, hey, we're out of here, there you go. So, here's the most important thing, and you can set this up different ways. So fundamentally at the day, one thing you can look at this, and I said, okay, if I have 6 moles of hydrochloric acid, how many moles of aluminum am I going to need to react with that? Oh, 1, because this is a 6-to-1 ratio. I got 6 moles of hydrochloric acid, I need 1 mole of aluminum. And then I could say if I have 6 moles of hydrochloric acid, oh, I can produce 2 moles of aluminum chloride. I can produce 3 moles of hydrogen gas. Now here's a common misconception that I want you to get out of your minds. My coefficients on the left side, if you add those together, you get 7, okay? If I add them together on the right side, I get 5, okay? So I don't balance with the sum of the coefficients. What I would balance with is the sum of the masses. So if I have like 2 grams of aluminum reacting with 4 grams of HCl, well, it would be 6 grams total. That means everything over here, if I could collect all that mass afterwards, would still have to add up to 6 grams. Okay? So don't confuse like a sum of masses with the sum of coefficients. Okay, completely different things. Related, but really not the same. So if you look on number 14, okay, so I want to make sure just everybody's cool with how I want 14 done. And I cannot tell you this enough, I cannot stress it enough. Stoichiometry, if you follow the rules, is not that difficult. Where you run into trouble is that you try and get cute and you try and take shortcuts, okay? That is the absolute death knell. The more you write down in terms of not only grams, but also is it aluminum, is it hydrochloric acid, is it hydrogen? Because we're going to get more and more and more complicated. And if you can't keep track of what those are, and all you want to do is write down numbers, because you think, well, that's all I need is numbers, okay? You're missing the whole point. This is a very complex process. And the more information that you have, the less likely you are to make mistakes. Okay, that's just the reality. So if you look at what's happening on 14, okay, you've got 54 grams of aluminum. So on any of those stoichiometric problems, you're always going to be given something, okay? It might be moles, it might be grams, it might be a volume of a solution, it might be the volume of gas. You are going to be given something. So in this situation, you've got 54 grams of aluminum. Okay, that's what you start with. That's what you were given. I've got 54 grams of aluminum. So if you're a visual person, okay, you're up here in mass, and here's parts, okay, and here's moles, and then you got another type of moles, and then you have mass, and then you have parts. And we're going to add on to this today. Okay, we're going to add on to this mole. So basically what you're doing is you're starting up here with 54 grams of aluminum. So if you're a sequential person, think this through. And this is the beauty of this map. You're going, oh, I got 54 grams of aluminum. I'm starting up here. The first thing I've got to do is convert from grams of aluminum into moles of aluminum. That's the first thing I've got to do. If I can't do that step, I'm dead in the water. I can't do anything else. But then that's going to get me into moles of aluminum, and then I want to go from moles of aluminum into something else. And when I do this conversion, I look at the periodic table. When I do this conversion, I look at the coefficients. Okay? That's it. So if you're a visual person, and you like, okay, hey, where am I at, and where am I going to end up, let this be your guide. But here's what's important on this mole. What you cannot do is you cannot go from grams of aluminum straight over here. You have to go into those moles of aluminum, and then you take those moles of aluminum and you roll that into something else. Okay, so the first thing you have to do, and this is why it's so important that you write down units. Oh, what am I starting with? 54 grams. Great. Hydrochloric acid, aluminum, hydrogen, what do I have? If you don't know what type of grams those are, you don't know what type of moles you have. If you don't know what type of moles you have, you don't know how to do that conversion. So that's why it's so important that you write down not only is it grams, but what is it? Is it aluminum? Is it hydrochloric acid? What is it? Okay, so I got 54 grams of aluminum. So, and again, here's the ultimate rule. Whatever units you start with up here is whatever units you put down here. There is no exception to that rule whatsoever. If you have grams of aluminum here, you have to put grams of aluminum here. I can't put grams of hydrogen, hydrochloric acid, squirrels, penguins, peanut M&Ms, nothing. The only thing I can put down here are grams of aluminum. That's it. Nothing else. That's it. It's rule. So, I'm going to put grams of aluminum here, and then that's going to be equal to 1 mole of aluminum. So if I look on my periodic table, that's 27 grams. So if I stop right now, miles, if I take 54 and divide that by 27, I get 2. Okay? But what does that 2 represent?
How many moles of aluminum?
Fantastic. At this point, I'm saying, hey, I'm going to react 2 moles of aluminum. Okay, that's what that step tells me. I'm sitting here right now in this location. I'm in moles of aluminum. Okay, so no matter what I want to end up with later on, I'm in moles of aluminum. Now, here's another common mistake that's made. What you'll do, and don't do this, and you'll all sit there and go, Mr. Burkamp, we won't do that, and you lie. Okay? What you try and do is you try and expedite the process. What you're tempted to do is, let's say, for example, there isn't, but let's say there was a 2 in front of the aluminum. There isn't, but let's just say there was a 2. Sometimes I've seen kids do this. They'll go, oh, 27 grams. They'll look up there and go, oh, that's 2 moles of aluminum. Okay? No, Miles.
There is a 2 in front of the aluminum.
Is there?
Yep.
Okay, there is a 2. I can sit right now. There is a 2. Okay, I was psychic. That's what I was thinking. So here's what what I've seen this done. Don't put the 2 here, okay? And here's the reason why. This is an equivalent statement. 27 grams of aluminum is only equal to 1 mole. It doesn't equal 2 moles, okay? It only equals 1 mole. So when you, listen to me. When you do anything with molar mass, okay, 27 grams if it's aluminum, 12 grams if it's carbon, whatever it is, that is only equal to 1 mole. So when you put grams here, you'll only put 1 mole up there. Okay, that's it. You will only put 1 mole, because that's what that's equivalent to. That relative atomic mass in grams is equivalent to 1 mole. Okay. Now, Miles correctly said, hey, if we stop right now, we have 2 moles of aluminum. Cool, it's fantastic. But now you look at this and go, oh, I want to know how many moles of hydrochloric acid I'm going to need to react with this. So I'm going to put moles of aluminum here. So now I'm going to put moles of aluminum down here. Okay, cool. And again, here's the deal. Whatever units you have here is whatever units you put down there. No exceptions to the rule. Now at this point you go, ooh, what do I want to change that into? I'm going to cross this bridge from aluminum and hydrochloric acid. Now I'm going to look at the periodic table. Now I'm going to find this coefficient. Oh, that's going to roll that into moles of hydrochloric acid. So I'm going to come up here, I get 6 moles of hydrochloric acid to 2 moles of aluminum. And that's where this ends, right here. Okay, I'm done at that point. Because my grams of aluminum will cancel out. My moles of aluminum will cancel out. I get moles of hydrochloric acid. Okay? So if you do this, you get 6 moles of hydrochloric acid. So what that means is if I have 54 grams of aluminum, I have to have 6 moles of hydrochloric acid to react with those 54 grams. Okay? Everybody cool with this? Like I said, this is not difficult. You can do it. Just don't try to get cute and shortcut it. Now, when you get to number 15, okay, so this is where we're going to add on to the model. So down here, we could also have a pool party. Okay, so there's a pool story. And that pool is measured in molarity. Okay? Now, flash back to molarity. At the end of the day, molarity means what? What per what? Moles per liter. Okay? So this is moles per liter. Okay? That's what this means. Moles per liter. Same thing over here. Moles per liter. So on 15, okay, you're saying, all right, I'm going to measure out 25 milliliters of 0.5 molar solution of hydrochloric acid. How many moles of HCl are present in the 25 milliliters? So here's the deal. So you have 0.5 molar solution of hydrochloric acid. So start with this idea. So this is the flashback. Okay. That means that I have 0.5 moles per 1 liter, which is the same depending upon your preference. You could also say that's 0.5 moles per 1,000 milliliters. So now we're back into conversions. Remember, 1 liter is 1,000 milliliters. It's the same thing as 1,000 cubic centimeters. I don't care how you write this. You can say 0.5 moles per 1 liter, which is equal to 0.5 moles over 1,000 milliliters. I don't care. It's up to you. It's personal preference. Pick one. Okay? Pick one. Now, think this through. I'm only going to measure out 25 milliliters. So, am I going to have more than 0.5? I'm only measuring out 25 milliliters. Okay? Not very much. I'm going to measure out 25 milliliters. So, Emma, when I measure out this 25 milliliters, am I going to have more or less than 0.5 moles in those 25 milliliters?
Less.
Less. Because if I have 1,000 milliliters, I'm going to have a half a mole. I'm only gonna have 25 milliliters. So I'm gonna have less than 0.5 moles in that. So I know when I get done, my answer has to be less than 0.5 moles because I have less than 1,000 milliliters, okay? Now, there's two ways you can do this. This is what I would recommend. This is what I would recommend. I'd start off again and go, okay, I have 25 milliliters of hydrochloric acid. That's what I'm given, 25 milliliters. That's what I'm starting with. I got to get rid of the milliliters of hydrochloric acid. Well, I know this is my ratio. So this is 0.5 moles per 1,000 milliliters. Okay? Now look what happens. The milliliters cancel out. I'm left with moles of hydrochloric acid. There you go. Okay? Now, your other option is you go, oh, Bergkamp, I'm a purist, man. That's moles per liter. That speaks to me. Okay, cool. So the other thing that you could do is go, oh, 25 milliliters. There's 1,000 milliliters in 1 liter, okay, which gives me 0.025 liters. And then I'm going to take 0.25 liters and go, oh, that's a half a mole of hydrochloric acid per liter. So if you're a purist, okay, and you want to convert the milliliters into liters and then multiply that by the molarity, that's cool too, okay? This is probably more chemically correct because that's what you're working in liters. But if you go, man, I hate decimals. I just had a bad experience with them in 6th grade, okay? Well, fine. Put 25 milliliters per 1,000 milliliters, or 0.025 liters per 1 liter. Okay, it doesn't make any difference. You get the same answer. But you just can't cross them over. You can't say, oh, I have 25 milliliters, and then put liters down below. So pick who you're going to dance with. Are you going to dance with milliliters, or are you going to dance with liters? Okay? I don't care. Okay? If I had to pick you, pick one. I'd go with liters, just because that's more scientifically correct. But it's up to you. So your answer to number 15 should be 0.0125 moles of hydrochloric acid. So that's what you get. That's what you get when you multiply that across. Okay? Not very many. Because number one, you only have 25 milliliters, 0.5 molars, right? Okay? So that's how many moles that you have. Then, on 16, now we need to figure out, okay, how many moles of aluminum am I going to need to react with that? So on 16, here's the deal. This becomes your known value. That's 0.0125 moles of hydrochloric acid. Same process at this point. Oh, I have moles of hydrochloric acid. I'm going to put moles of hydrochloric acid down here. And then you're asked to figure out, oh, how many moles of aluminum are going to be needed? Okay. So then I'm going to put moles of aluminum up here. I'm going to go to my balanced equation. In front of the hydrochloric acid, there's a 6. In front of the aluminum, there's a 2. So I'm going to take 0.0125 times 2, divide that by 6, easy peasy, lemon squeezy. There's your answer. So it's going to be an even smaller number because you're basically dividing by 3. Okay? Grace?
Well, sorry. Me and I were talking about it, but what kind of equation is it? Is it single displacement?
Yes. Or you could put redox. Either one. Yeah, because you have an element and a compound producing a different compound and a different element. So you can either put single displacement or redox. Redox sounds cool. Now, let's talk, for example, on number 20. Okay? So, I want to work number 20 just to make sure everybody sees exactly how this is going to play out. So, here's the problem where it tends to flip people out on number 20. Because of the fact that you got 3.8 moles of hydrogen gas, and you see that as like the product, and it is. okay? And you tend to want to make that like the last step because, oh, hydrogen is at the end and that should be the last step in my conversion. It's not it at all, okay? It's not it. What we're saying is that it doesn't make any difference because this stoichiometry can go from left to right. You can work within just a ratio of products. You can work within a ratio of reactants. You can work in a ratio of reactants to products. You can work in a ratio of products to reactants. It doesn't make any difference, okay? This thing goes back and forth. It doesn't make any difference. But what's important is that it's always the same process, okay? So on number 20, set up this chart. And up here always goes what you were given in the problem. So on number 20, what you're given is 3.80 moles of hydrogen gas. I want to make this, okay? I got to figure out how many grams of aluminum chloride are also produced, okay? So I'm working everything on the product side. Reactants have nothing to do with this, okay? But it's the exact same process, okay? I got moles of hydrogen. I'm going to put moles of hydrogen here, okay? So it has nothing to do with mass at this point. I got to go from moles of hydrogen. So on the mole, here's where I'm at. I'm going from moles of hydrogen. The first thing that I have to do is go, what am I trying to find? Aluminum chloride. Moles of aluminum chloride. This has nothing to do with Avogadro's number. This has nothing to do with the periodic table. This is all about the reaction and those coefficients. That's all this is about. So, I go hydrogen, I go moles of aluminum chloride. I look at the balanced equation. There's 3 moles of hydrogen to 2 moles of aluminum chloride. So if I stop right now, if I don't do anything else, the moles of hydrogen have canceled out. I know how many moles of aluminum chloride I have. So if I was just asked, hey, how many moles of aluminum chloride are you going to produce? There's your answer. You can stop right there. You're done. That's all you have to do. Okay? That's it. Stop. But what are you asked to find? Moles or mass?
Mass.
Mass. So now I need to go, oh, now, here's what I don't want you to do, okay? Don't transfer 2 moles of aluminum chloride down here. You can transfer 1 mole of aluminum chloride, but don't move the 2. Move the units, not the number, okay? So I'm going to put 1 mole of aluminum chloride down here. It's cool. Now, if you're a visual person, now I'm going up to the mass. Now I'm going up to the restaurant. So I'm going from here up to here. So where am I going to look? What do I have to use at that point? Parker.
The periodic table.
Yeah, I got to look at the periodic table. Okay? And I'm going to find, that's AlCl3. So make sure when you do chlorine, make sure you're using 35.5. Don't round it up to 36. Don't round it down to 35. Use 35.5. So you take 35.5 times 3, and then you're going to add that to the 27 grams of aluminum, and that's going to get you 133.5 grams of AlCl3. So basically, you're going to take, mathematically, you're going to take 3.8 times 2 times 133.5. Okay? Then you're going to divide that by 3, and that's it. Okay? There you go. And you should get an answer, something in the 300 gram range. Okay. Let me see. Your answer to number 18 should start with an 8. Your answer to number 19 should be something around the square root of 4. Your answer to number 12 should also be something around the square root of 4. Your answer to number 11 should be around 100. That's an ish. Your answer to number 7 should be something around the square root of 25. Your answer to number 8 should be around 2. That's a huge ish, but it's around 2. And your answer to number 9 should be around 1. Okay? Are we good? Any other ones at all you want me to go over?
Oh.
Grace?
Yeah, so on the very first thing it says either a ratio of moles or a ratio of blank, but never a ratio of mass is what I read.
So it's either a ratio of particles or atoms, okay, or it's a ratio of moles.
Okay.
So it could be like 5 atoms of hydrogen react with 10 atoms of oxygen, or 5 molecules of something react with 5. So that particles is just like a generic thing. So it's either particles or moles, but it's never a ratio of.
Mass.
There you go. Okay. Anything else?
Yeah.
Going once? Going twice?
Sold.
That's my line. So stop that. So if you all nitrates are soluble, right? Sodium hydroxide, how do you know sodium hydroxide is soluble? Or sodium at? Which group?
One.
Group 1. All group 1s are soluble. Now we get aluminum hydroxide. Mr. Drill, find me the solubility rules for hydroxides. Or somebody find me, look at the solubility rules for hydroxide. Most hydroxides are actually insoluble. Okay? So, we got it, Mr. Grill. We're good. So, aluminum hydroxide is going to be my precipitate, right? Okay? So, is this balanced? Addie, is this balanced? Let me give you a hint. The answer is no.
No.
Because how many nitrates do I have here? How many nitrates do I have over there? So what do I need to do? Put a 3 here. Then what? Now am I balanced? Okay, it's cool, right? I'm balanced. Now, what I've done is I've expanded moles mole, and we've branched out even farther. Okay, so we've added on to the mole. So there's a pool store. Okay, that's going to be dealing with solutions. That's going to be molarity, which is moles per liter. We'll talk about this. There's also going to be a gas station. Okay, because a lot of times in reactions we produce hydrogen gas, we produce oxygen gas, we produce something. Okay, so if there's a gas station, you're going to need this number, 22.4 liters. So 22.4 liters is this. Okay, so if you have 1 mole of a gas, and this is going to be important, under what we call STP. Okay, STP stands for standard temperature and pressure. So standard temperature and pressure in gas laws, you don't need to know this, I'm just pointing this out. You'll learn more about it in Chem 2. Standard temperature and pressure for gas laws means that your temperature is 0 degrees Celsius, which is really, really cold, and the pressure is what we call 1 atmosphere of pressure. Okay, y'all have dealt with pressure before. Okay, we've done with this. So at standard temperature and pressure, 0 degrees Celsius, and a pressure of 1 atmosphere, any gas, doesn't make any difference. If it's hydrogen, oxygen, carbon dioxide, doesn't make any difference. Any gas, if you have 1 mole of it at standard temperature and pressure, occupies 22.4 liters. And this is a volume of 22.4 liters. So this is what 22.4 liters of gas would look like. So 1 mole, and you would have to be specified this. 1 mole, and I'm always going to do this, it's just going to be 1 mole at standard temperature and pressure, occupies a volume of 22.4 liters, and it contains 6.02 times 10 to the 23rd molecules. And again, this is the same no matter what type of gas it is. Hydrogen, oxygen, carbon dioxide, methane, ethane, doesn't make any difference. Any gas under standard temperature and pressure is going to occupy this much space. It's going to be 1 mole. It's going to have a volume of 22.4 liters. There you go. Okay. Now, so if there's a gas station, you're going to use 22.4 liters. If there's a volume, if a molarity, you're going to use moles per liter. If there's mass, you're going to look at the periodic table. If there's parts, you're going to use Avogadro's number. So, depending upon what you have, you're either going to use Avogadro's number, the periodic table, the molarity, or 22.4 liters. But no matter what, all roads lead to moles. Okay? They all lead to moles. And then you're always going to do some type of conversion over to something else, another type of moles. And then from there, you can branch out. You can go to mass. You can go to parts. You can go to volume. You can use the pool part. Okay? So I'm going to work at something about as complicated as it's going to get. Ella, you want to start with a mass problem or a molarity problem?
Mass.
Okay. All right. So here's the deal. So here's the reaction, right? Okay? So here's how this is going to play out. I'm going to say, all right, I'm going to react 2.50 grams of sodium hydroxide because Ella said she wanted mass. And what I want to know is how many grams of aluminum hydroxide I should produce as the precipitate. Okay, because aluminum hydroxide is my precipitate, right? There we go. So it's insoluble. So visualize this. I'm going to give you a beaker, and you're going to measure out 2.5 grams of sodium hydroxide. You're going to pour that in there. Boom. Then you're going to add some aluminum nitrate to it. You're going to make a precipitate. And then, based upon this, I want to know what we call our theoretical yield. How many grams of aluminum hydroxide should I be able to produce from 2.5 grams of sodium hydroxide? So this one is important that you realize where you start and where you're going to end up. So if you're a visual person, I'm starting here with grams of sodium hydroxide. So, I'm here. I'm going to look at my periodic table. I'm going to get moles of sodium hydroxide. Then I'm going to cross from moles of sodium hydroxide over here into moles of, in this case, aluminum hydroxide. I'm going to look at the balanced equation. So I'm going to go mass. I want to look at the periodic table. That's going to get me moles of sodium hydroxide. Then I'm going to look at my balanced equation. That's going to give me my moles of aluminum hydroxide. Then I'm going to go, Ella said she wanted mass, so I'm going to look at the periodic table again. So in this sequence, I'm going to look at the periodic table twice. I'm going to look at the equation once. So I'm going to go twice I've got to reference the periodic table, once I've got to reference that. So if you know ahead of time, this is where I've got to go to look at that information, that's handy. Because then you know, okay, I got to look at the periodic table twice, the equation once, hey, I'm off to the races. Okay, so this is going to be one big, long conversion. So I'm going to start here with 2.5 grams of sodium hydroxide. Peyton Queen, the Mad Hatter. I have grams of sodium hydroxide up here. What am I going to put in the bottom right?
Grams of sodium hydroxide.
Grams of sodium hydroxide. Okay? Where am I going to look to get the grams of sodium hydroxide?
Periodic table.
So, what's the molar mass of sodium? 23. Hydroxide is 16. Hydrogen is 1. Add all that up, you get 40 grams. So I got 40 grams of sodium hydroxide. Now, does 40 grams of sodium hydroxide Luke Etheridge, is 40 grams of sodium hydroxide equal to 3 moles of sodium hydroxide? Because there's 3 in front of the sodium hydroxide. Or is it only equivalent to 1 mole of sodium hydroxide? Do I put a 3 or do I put a 1 up there where I go to moles of sodium hydroxide? 3 or 1?
3, 1, a 1, a 1.
You did exactly what I told you not to do. This is why you have like this visual reference here, right? Anytime, listen to me, listen to me, listen to me, listen to me. Anytime you are doing a mass to mole conversion, you only ever use 1 mole. That's it. That 3 has nothing to do with that. That could have been a 12. It could have been 500. Wouldn't make any difference, okay? 40 grams is only equivalent to 1 mole. That's it. It's only equivalent to 1 mole. Nothing else. 1 mole. So I'm going to put 1 mole here. Okay? 1 mole of sodium hydroxide. If I stop right now, Carter Smith, what units am I going to have? If you get this wrong, so help me, I'm just going to lose everything.
Moles,
Of what?
NaOH.
Sodium hydroxide. Fantastic. So at this point, I am here at the mole. I have landed at the mole. Now I need to go from here over to here. Emma, where am I going to look? To go from one type of moles to the other type of moles.
The equation.
Yep, now I'm going to look at the equation. So I'm going to put moles of sodium hydroxide down here, and I'm asked to find how many grams of my precipitate I can produce. So I'm going to put moles of aluminum hydroxide up here. So I'm going to put moles of aluminum hydroxide here. Now, Emma's saying, oh, Mr. Burkamp, now we need to look at the equation. And we do. So now we're going to go, 3, because that's what, now I'm going to use the 3, okay? In front of the aluminum hydroxide, there's a 1. Carter Smith, if I stop right now, what units do I have?
Moles,
Of?
NaOH.
No?
No. Oh, wait.
Moles of sodium hydroxide are canceled out. They're gone.
KLOH3.
Yeah, moles of aluminum hydroxide. So if I stop right now, I know how many moles of aluminum hydroxide I've produced. Cool with that? Got it. But that's not what I'm asked to find. I'm asked to find my grams of aluminum hydroxide, right? But here's the deal. I have aluminum hydroxide here, so I'm going to put moles of aluminum hydroxide down here. Okay? Now, 1 mole of aluminum hydroxide, so if you go up here to this schematic, I'm here at moles. Okay? I'm here. I want to go up here to mass. Raman, where am I going to look?
Periodic table.
Now I'm going to go back to the periodic table. Oh, okay, right. So, my aluminum hydroxide, which is AlOH3, okay? And again, this is where so many things get tied in together. Oh, you got to remember, oh, aluminum hydroxide, aluminum is 3+, hydroxide is 1-. You can do all the stoic in the world. If you can't write the formula for aluminum hydroxide and AlOH3, you're dead in the water, okay? That's why you have to be able, this is why this is so sequential, and this is why this is like the culminating thing. So if you want to get clever, you can go, oh, oxygen is 16, hydrogen is 1, that's 17. There's 3 of those, and then, so, Addie, do us a favor, take 17 times 3. 51?
Yes.
And then aluminum is 27, so we get 78. grams of aluminum hydroxide. Okay? So, here's where the magic happens. This is why I said these problems get so complex. Grams of sodium hydroxide cancel out. Moles of aluminum, or moles of sodium hydroxide cancel out. Moles of aluminum hydroxide cancel out. I have the only thing left, which is grams of aluminum hydroxide. So at this point, I'm going to take 2.5 times 78, and then I'm going to divide that by 40 times 3. Now, if you're going to do this, some people like to divide and conquer. What they'll do is they'll multiply everything by together, and then they'll get an answer. And then they'll multiply everything by the bottom and get an answer. And if you do that, that's cool. Just don't round those numbers when you multiply them together. Keep all of those digits, okay? Don't round until you get to your final answer. So that's roughly, I don't know, 80 times 2 is 160, 200, I don't know, 2 something, roughly. What do you get?
1.625.
What'd you get?
1.625.
I wasn't too far off, just a ballpark. So 1.625. So we'll call that 1.63 grams. So here's what should happen. This is what this would physically look like. I'm going to give you a beaker, and you're going to put in 2.5 grams of sodium hydroxide. You're going to add some water to dissolve it because of the fact that this is a double displacement reaction, because that's what all I wanted was a double displacement reaction. So the sodium is now floating around, the hydroxide is floating around. Boom, we come along here and we add the aluminum nitrate to it. So I'm going to give you a beaker, you're going to add aluminum nitrate to it, boom, here you go. You're going to see a chunky white precipitate form of aluminum hydroxide. That's your precipitate. So if you filtered that out, okay, if you took this and you filtered it out and you let it dry, this tells you how many grams of aluminum hydroxide you should have as that precipitate. Okay, that's what we call our theoretical yield. This is what you should get. So, now some people like a fill-in-the-blank approach. Okay? Here's another option. Some people like this approach. I'm giving you options. So as long as it is just a mass to mass conversion, here's your sequence. This is going to be some given mass. Okay? Whatever it is here. Down here, you're going to put the molar mass of whatever that is. And that's going to be 1 mole of your given. Okay? So the only thing that changes in this first step is this molar mass and how much mass you're given. Then you're going to put moles of given here. And then up here you're going to put moles of need. What do you need to end up in? Okay? And this is going to go, this ratio is going to come from your equation. And then you're going to put 1 mole of what you need down here. And then you're going to put the molar mass of what you need up here. Okay? So, the only time in this sequence where you're not going to use 1 mole is this ratio right here from the equation. So if you like this, like, oh man, this is kind of cool. Here's kind of a standard format. So this is what we just did. We put the 2.5 grams of sodium hydroxide here. We put the molar mass of sodium hydroxide here. That's 1 mole. We looked and we found, oh, here's the ratio of moles to aluminum hydroxide. We looked at the equation. Then we put 1 mole of what we needed, which was aluminum hydroxide, and then the molar mass. So, now, here's another thing that you can look at this. But wait, there's more. Basically, you go, the first bit of information that you find is from the problem. Okay? What did Burkamp type up in the problem? That's where you're going to find this first bit of information. Then you're going to look at the periodic table, then you're going to look at the equation, then you're going to go back to the periodic table. So you're going to go problem, periodic table, equation, periodic table. So if you like that thought process, like, ooh, where do I go to find that information? Problem, periodic table, equation, back to the periodic table. Okay? So if you like that thought process, that's another way that you can think it through. Okay. Do one more. Ethan, zinc or magnesium?
Zinc.
Okay, so I'm going to take a piece of zinc and I'm going to drop that into hydrochloric acid. Right away, what type of reaction is going to take place? Zinc displacement. Zinc is more reactive than hydrogen. It's above it on the reactivity series. Zinc's going to kick out the hydrogen because the hydrogen comes along and says, yo, sup, give me your electron. Zinc says, fine, I don't want any. Take Eddie and Edna. I'm going to get zinc chloride and hydrogen gas. I'm going to balance this. I'm going to put a 2 in front of this. Okay? So, Miles, pick a number between 2 and 5.
3.
Huh?
3.
Okay. So we're going to react 3 grams of zinc. And I want to know how many liters of hydrogen gas I should produce. Like, ooh, this is a new twist. We haven't talked about volume of gas produced. This is kind of cool. Okay? But if you go back to this visual of this, go away. So now, this is where this is going to get a little bit different. Same idea. We're going to start with grams of zinc. We're going to change that into moles of zinc. We're going to take moles of zinc and we're going to change that into moles of hydrogen. But now, because we want to find the volume of gas that's produced, now I've got to go down here to the gas station and I'm going to use the 22.4 liters. Okay? So I'm going to go from mass, look at my periodic table, get into moles. Look at my equation, go to a different type of moles. I'm going to go down here to the gas station and I'm going to use this value of 22.4 liters. Okay? So, Miles said he wants 3 grams of zinc. Cool. So I'm going to put grams of zinc here. Now, that's going to be 1 mole of zinc. So somebody find me the relative atomic mass of zinc.
63.5.
63.5 grams of zinc per 1 mole. If I stop right now, what do I have, Carter Smith? Moles of zinc. I'm going to end up in hydrogen, right? So I'm going to put moles of zinc here. I'm going to put moles of hydrogen up here. That's 1-to-1 ratio. So however many moles of zinc that react is how many moles of hydrogen I'm going to get out of it because it's a 1-to-1 ratio. Okay? There you go. Now, down here I'm going to put 1 mole of hydrogen. Now at this point I have options. If I had said, how many grams of hydrogen gas am I going to produce? I would put 2 grams of hydrogen up here because that's the relative atomic mass of hydrogen. If I said, how many grams of hydrogen, I would put 2 grams up here. But here's the problem. When you collect gas, it's really, really difficult to measure the mass of a gas. Mainly because it's always mixed with air, and then it's like, okay, are you measuring the nitrogen and oxygen with it? How do you just separate the hydrogen? Because it's in air, and it's complicated. Volume's easy to measure. Oh, I let it bubble up through a gas, it's called a gas collection tube, and you figure out, oh, how much volume of hydrogen gas did I produce? And there you go, okay? So, because I'm asked to find volume of hydrogen gas, I'm going to put 22.4 liters here. Okay, standard temperature and pressure. So the magic happens. The grams of zinc cancel out. The moles of zinc cancel out. The moles of hydrogen cancel out. I get liters of hydrogen gas. So somebody take 3 times 22.4 and then divide that by 63.5.
1.058. That's what I got.
Okay. 0.058?
1.05.
Oh, okay, that sounds a little bit better. 1.058, so call it 1.06 liters. Okay, so to give you some perspective, it'd be about enough to fill up this bottle right here. So this is about a liter. So this is how much gas that you would collect out of this reaction. Now, here's what's also implied within this. What's implied within this is that we have enough hydrochloric acid so that what happens is that reactions take place until something runs out. So what we're assuming is that we've got a whole bunch of hydrochloric acid, and as soon as the zinc runs out, the reaction stops. Okay, so we're assuming that we have heaps and heaps and heaps of hydrochloric acid. As soon as the zinc runs out, the reaction stops, because something has to, that reaction is going to go until something runs out. Either until you run out of zinc or you run out of hydrochloric acid. So what we would do is we would overload that beaker with a whole bunch of hydrochloric acid, so that as soon as those 3 grams of zinc ran out, boom, we stop. Now, let's say, and here's as complicated as these problems get, and then I'm done. So we're going to react zinc and hydrochloric acid to get zinc chloride and hydrogen gas. Okay? Balanced equation, old school. We're still going to go back to the 3 grams of zinc. Now, here's what I want to know. I'm going to have a beaker full of a half a molar of hydrochloric acid. Okay? Got a beaker. Got 0.5 molar hydrochloric acid. Okay? So what I want to know is what volume of hydrochloric acid of 0.5 molar would I have to react exactly with 3 grams of zinc. Okay? So at this point, I'm not going to use the 22.4 liters because this isn't a gas. Okay? You only use the 22.4 liters if it's a gas. Hydrochloric acid is not a gas. You've always seen hydrochloric acid. It's a beaker. It's liquid. It looks clear. It looks like water, right? But it's the exact same process. So basically what's going to happen is this. If we go way back up here, I'm going to start with 3 grams of zinc. I'm going to change that into moles of zinc. I'm going to take moles of zinc. I'm going to change that into moles of hydrochloric acid. Now, at this point, I'm going to go down here to the pool store, okay? Because now I'm dealing with molarity, which is moles per liter. So I'm going to go periodic table, moles. Look at the equation, get another type of moles. I'm going to go down here to the pool party. Now I know I have to use moles per liter, okay? That's why I said, if you have this visual, you know, I'm going to go periodic table, moles. Different kind of moles. I'm going to end up at the pool. Now I got to use moles per liter. That's the beauty of this visual approach. Okay. So it's going to start off the same way. So I'm going to start off with 3 grams of zinc. We said the molar mass of zinc was 63.5 grams of zinc. Luke Etheridge will attest that 63 grams of zinc is only equal to 1 mole. Now, I'm going to deal with my hydrochloric acid. So there's a 2 in front of that hydrochloric acid. So I'm going to put 1 mole of zinc because that's the coefficient. Then we're going to put 2 moles of hydrochloric acid. So Carter Smith, if I stop right now, what units do I have? Moles of HCl. Grams of zinc are going to cancel out. Moles of zinc are going to cancel out. I have moles of hydrochloric acid. Now, I want to show you two ways that you can do this from this point, okay? This is a personal preference thing. So somebody take 3 times 2, otherwise known as 6, and divide that by 63.5 grams of zinc. So take 6 and divide it by 63.5.
0.094.
0.094, then what?
48.
So it's 0.94, then what? What's after the 4?
Oh, just 4888189.
So call point 0.0949.
Yeah.
You want to do not, if you're going to do it this way, you keep a lot of digits. Do not write this as 0.09. You keep a lot of digits. Now, what that represents, like Carter just said, that's how many moles of hydrochloric acid that I'm going to need. So this is what you can do. This is a personal preference thing. I want to show you an option. One option is that you know that molarity. So that means I've got 1/2 of a mole per 1 liter is going to equal 0.0949 moles over X number of liters. Okay, that's what that means, because this means moles per liter. Okay? I only need 0.094 moles of this stuff. So is this number here going to be bigger or smaller than 1 liter? Keep. Smaller. I don't need 1/2 mole. I don't need that much. I only need 0.0949 moles. So I'm going to take 1 times 0.0949 and then divide that by 0.5. It's a ratio. So somebody take 0.0949 and divide that by 0.5. 0.1.
898.
So actually we're going to round this to 0.190 liters, which if you multiply by 1,000 would be 190 milliliters. Okay? So if you like ratios, you go, Burkham, I am the king of ratios. I was president of the ratio club at Mays High School. Fantastic. Set it up as a ratio. You go, Mr. Burkham, I like cancellations. I like stoic. Okay, fine. Your other option is that you come over here and you got moles of hydrochloric acid. So I want to put moles of hydrochloric acid down here. Now, this is where this gets a little bit wonky, but it's not bad, it's just a little bit wonky. You have molarity, which is 0.5 moles per liter. So what you're going to do is this. It's a little bit wonky. Some people like this, some people it just flips them out. You know that this is 1/2 of a mole. What this means is that that's 1/2 a mole per 1 liter. Now, the beauty of this is that you make all of the units cancel out. But what's weird, and this is the leap of faith that you have to take. You've got to take the molarity and you have to flip it over. Because you're going, oh man, Burkham, since we've been talking about molarity, you've always said it's moles per liter. And I have. Okay, I've preached that to you. I have. But in this situation, to make the units work out, I flipped that over. But it's cool though, and here's the reason why. Then my moles of hydrochloric acid cancel out. The only thing I have left is liters, and that's what I want. So this works, but you have to think a little bit backwards, and you have to flip over the molarity. If you don't like that, if you go, Burkham, that's weird, I can't do that. Fine. Get the number of moles of hydrochloric acid, then set it up as a ratio. Okay? I don't care. I'd prefer this, because it's all just one step. But that's a personal preference thing as far as how you do that. Okay. I'm done. So stop that for a second. Okay, so this one combines everything that we have done, okay? So you're going to have moles, you're going to have grams, you're going to have volume, 22.4 liters, you're going to have molarity, okay? It is a smorgasbord of conversions. Now, let me give you a hint when you get down to the middle of the page. And it's gonna say, write and balance the reaction to describe the combustion of methane with oxygen to produce carbon dioxide and water. Because if that equation is wrong, then everything is going to be wrong, okay? So when you get done with that equation, you should have a couple of 2's for coefficients, okay? So you should end up, for example, you should end up with a coefficient of 2 in front of the water, okay? So if you do it right, I'm not saying that's the only 2, but that's at least going to tell you if you did that right, okay? The other ones, I've given you the equations, okay? And this is going to tie in even net ionic equations. This is going to go a whole bunch of old school things. So, anyway, you're on your own. Be free. All right, Miles, stop that. We'll call